have access to it. All right, welcome back, everyone. How are we doing? Still safe. Here it's going to get pretty bad these next couple of weeks, so just please be safe out there. 6 feet at least, right? Social distancing. So I mean, your health is more important. So please be careful out there. All right. So our goal today is to finish off a strain, right? So we started it out. Now we're gonna finish it today, chapter 2, and then we're gonna move on to chapter 3. Initially, at the end of last Monday's lecture, we were talking about what strain is, right? So even before that, chapter 1 was what stress was, right? So stress is like the internal forces and moments, and what do they do to the material, right? What do they do to the actual cube? Forces that are normal will kind of stretch out the cube. Like it has a stress, it's called normal stress, right? The N over A, right? When forces are on the surface, they tend to shear the surface, right? And you have it's what it's called a shear stress, right? So the difference is when you cut something, right? That when you cut something, you have a normal, and then you have a shear, typically, right? So you have normal forces and shear forces. So now chapter 2 is talking about geometrically what is going to happen to the material. Think of, and I want to make a connection to actual to what do you call it? Something you know. This is, what is this equal to? What is this? Anyone? Huh?
Dynamics.
Dynamics. Or what's the word for this one? What's the word for this?
Second Newton's law.
Yes, Newton's second law, right? So this is a measurement. When you look at how forces are acting on bodies, and then how they move, right? So if you notice, this is very similar to what we're talking about now. So typically what's happening in materials, you're talking about materials, these forces act externally on bodies, right? Typically forces act externally on bodies. What we're talking about is internal forces, right? What is happening to the cube inside? But mathematically, it's the same thing, right? It's force over some area. So, but remember, force is what's acting on it, right? And what is acceleration? Acceleration is like the description, right? The geometric. Get more real estate screen space over here. So it is geometric description of movement, right? Description. Another word for that, again, for those of you, sorry, my writing is a little off right now. Another way of saying that is called kinematics, right? Over here, this is when you package the force and the acceleration, right? That's called kinetics. This is just kind of reviewing from before. What is a resistance to translation? Inertia, right? Inertial mass. Yeah. Okay. So very similar to what we're talking about now, because what chapter 3 is going to talk about is, well, look, you have a force. Let's take a spring, right? I'm just kind of giving you a big picture because we'll go into the details of solving things and all that. Typically, when you have a spring, what do you do with the spring?
Stretch it.
Stretch it or
compress it.
Compress it. Okay. So you stretch it by some force, right? And then what happens to the spring afterwards?
Retracts.
If you stretch it?
Delta change.
And for those of you that are taking circuits, it's not a resistor. So the actual spring is going to get longer, right? So if I look at that, well, doesn't your spring, and you probably did like a physics lab on this, isn't your spring, doesn't it have an initial length, L naught?
Yes.
And then doesn't it have some think I canceled something. Oh, maybe. Okay, are we back? Something happened here. Okay, so now doesn't have, it should have some initial length, and then shouldn't it have some final length, right? But don't we care about when is there force? There is no force when the spring is not stretched, right? So what we care about is its change in length, right? And you actually got data. You would in your physics, you would actually plot. You would plot the force and then like your change in length, or you call this delta x, right? So you would get some data, right? And then from this data, you would actually find the slope, right? And what is the slope equal to? Zoom in here. What is that slope equal to?
Spring constant?
Yes, that's called the spring constant. So there's a mathematical relationship in which you relate the force to the geometric description of stretching, right? So the same idea. And that mathematical model is well, look, it's a linear spring, right? So that means it's going to be a linear function. And in general, linear functions are y equals mx plus b, right? If there is no force, there is no displacement or change in length. So that's why the y-intercept is 0. So just replace your y with your force. The slope is your spring constant, and then your x is like your change in length. It has to be change in length because when you have a force is when you displace it, right? If you're not, the spring, if you're not pulling it, you're not going to have some change in length, right? So there's no force. So now, but look, how do we model materials, right? What if I have, I'm going to try my best. No, they're not resistors in parallel. What am I doing here?
Lagging.
Huh?
Lagging.
I'm lagging? Am I really lagging?
Yeah.
Writing's like super delayed.
Oh no. I'm going to have to. Okay, I'll slow down.
It's showing right now.
Okay. Yeah, sorry about that. Let me actually, but I want you to conceptually see what's going on. So these green highlights that you'll see eventually are going to be atoms. Okay? Materials, solid materials is not made of one spring, right? The way we think about atoms, the way they're connected is that they're at some equidistant or some neutral point, right? Some equilibrium. You learn about that in material science, right? What is the actual separation distance, the bond length? But what I care about is there's a network of springs, right? And when you look at a material, there's a lot of atoms and springs connected together. So I can't really look at the force over one spring, right? Let's say this is a material and I pull it this way, right? Some force here. What you need to do is look at it over some area, right? Isn't that when we cut things, didn't we cut some area? So what we're going to do is get that same formula, right? The spring constant, but over some intensity, over some area, right? And then what we're going to do is look at, well, if this is a block of material, we're going to divide by some starting distance, okay? Some starting distance. L naught, okay? So, but remember, K is reserved for one spring, right? So if I look at this plot, right, all I'm doing is this. If I look at the plot, F over A, you see that? To change the length, all I got to do is divide by the original length. What's going to happen is those are your formal definitions, right? These are actually your definition for chapter 3. Sorry, it's like it's jumping right now. What is F over A? F over A is like my normal stress, right? My change in length over my original length is my normal strain, which is something that I'm going to go back to in the slide at the beginning, right? And how stiff of the material is, right? Because isn't K the spring constant? It's how stiff the spring is. But if I have a lot of springs, I need something equivalent to how stiff a material is, right? That material, that constant is going to be E, Young's modulus, okay? So this is only specifically for normal stress, okay? And I'm summarizing 3 things, right? This is chapter 1, right? This itself is chapter 2, and this whole thing together is chapter 3. Does that make sense? If you guys want to do some thumbs up on your, I gotta maximize this to see who's in here. I got 1 thumb up. Okay, I got quite a few. All right, awesome. Cool. So that's essentially what we're doing. But look, chapter 2, we're just focusing on epsilon, right? So let me go back to what we summarized last time at the beginning. Then we'll start solving some problems. And well, actually, there's a small derivation. What is the infinitesimal strain, right? So let me go back. So over here. So what we said was normal forces will stress the material, right? So if you look at the normal force right here. So let's say I have a block of material here, right? Originally I draw a green line on there, and I measure the length of the green line, right? So the length of the green line is L naught, L initial. Same idea as a spring, right? But then what happens if I apply force on this block of material? Shouldn't the green line extend, right? Shouldn't it stretch out? Since the force was normal to it, causing a normal stress, right? It should lead to a normal strain. That's what epsilon is, right? And remember how I told you from the spring, don't I care about its change in length in order for you to have some resistance, right? So the material can push to resist. The resistance to pulling is called Young's modulus. We're not going to learn that yet, right? It's how we tie the stress and strain together. That's called Hooke's law. But however, change in length is always final length minus the original length, right? And then we have to normalize it. We have to divide by its original length. Okay, that's just the definition. Because no matter, it's relative to its original, right? You can have a bigger line segment, but as long as you divide it by its original length, it's going to be the same strain, right? Meaning, if I have a longer L initial, and I'm going to have a longer length after, right? But don't I care about the relative strain, how much it changes? Shouldn't that be the same? Should that be the same change in length, right, relative to the original? So both line segments will stretch out, will strain the same amount, even though they're different lengths to begin with, okay? That's why we divide by its original length, all right? Now, when you cut something, you have a shear force and a normal force, which is N, and you also have a, make sure I get my shear force. Shear force, good. So geometrically, what do shear forces do, right? And notice that down here, right, shear forces are on the surface. You have to have 4 of them on the surface, at least in 2D, okay? So in 2D, the shear force is why? Because static equilibrium, right? If a force on the right side is down, you have to have an equal and opposite force up. But this is a force couple, so you need a force in the top side and a and an equal and opposite force on the bottom side. Because don't you create a moment, right? And that's the unique thing about solid materials, things that are solid, that when you shear materials and you let go, they'll bounce back, right? Try to get gas or water, right? When you shear a water, right, you get some water in your hand, do it now, preferably over your keyboard. Get water and shear it, put a force on it. Will it bounce back? Right? It's not, right? That's why when you look at water pressure, the only type of pressure you have is hydrostatic pressure, which is forces on the normal directions, not shear, because water cannot sustain shear. Another thing, earthquakes. Earthquakes have two types of waves. When you guys do civil engineering, the ground shakes two ways. There's sound waves. Remember when I talked to you, there's sound waves. Those are compression waves, right? Another word for saying that. And you guys did some labs in physics. Those are directional. Those are vibrating toward you. But then in sound, there is no shear waves, oscillations. The ground actually shears, right? And the shear stress, when it travels as a wave, get a slinky, right? You know those slinkies? The slinkies, okay? What happens if you hit the slinky this way? It's going to compress, right? But now what happens if you do this to the slinky? You create a little wave, right? You move it up, right? And then you move it down. You get the slinky, you move it up and down. That's called a transverse wave because the particle goes up and down, right? It shears. So when earthquakes happen, you have a P wave. It's called a compression wave in the actual earth because it's more of a solid. And then you have the slower shear waves. And what happens when you have shear waves, they're slower, and buildings tend to move slowly. They have a natural frequency that's slower. And so that's why engineers have to design against the shear wave, because they can create crazy vibrations, right? And that's why they dampen a lot of the structures. So that's just a side thing, right? But right now we're doing static equilibrium, meaning I'm not creating waves, right? I'm just pulling it and loading it statically. I'm holding it, right? I'm not creating a wave like that. So that's just a side thing, okay? Does that make sense? So solid materials have the ability to shear. So going back to the picture, right? So what does it do geometrically? So the actual shear forces are on the surface, right? They will actually change, not its length, but change its angle, right? So that variable, that angle change, so notice how normal strain has epsilon, shear strain has gamma. Get a textbook or a folder, right? Or anything, a stack of papers, a deck of cards. If you put a force on the surface, don't you change its angle, right? If you do this, you change its angle. So try that on your own. So what it's going to do is change its angle. And that change in angle, so see how before, look at the box, right? Initially your box was 90 degrees, right? Your box was 90 degrees. That's your initial angle. And look, how do you measure angles? You have to measure with respect to two coordinate systems, right? You have to measure with respect, like for example, in this case, this is the X and Y. They have to be perpendicular. So then, because that's how you measure angle. So shear strain is based off of angle, okay? So there's an initial angle of 90 degrees, but then don't you have a new angle right here? That theta prime is your new angle. But what do we care about? We care about change in angle, okay? So just like change in length, we care about change in angle. That change in angle is called shear strain, all right? So shear forces lead to shear stress, which causes geometrically shear strain. It's a change in angle. And our goal for chapter 2, is focus on this definition, right? This definition, normal strain, and how we calculate shear strain, which is based off of this definition here. How do you relate them? Just to kind of foreshadow already chapter 3, how do you relate them? Normal stress is related to normal strain with Hooke's law, Young's modulus. Shear stress, right? Which again, let me define it over here. So normal stress, and I'm gonna rewrite this, right? What is sigma? Normal over the area. What is Young's modulus? E. And then what is strain? Change in length over original length, right? I just kind of expanded it. This is going to be very important for chapter 4 also. Shear stress is equal to shear strain somehow, right? But don't you need some resistance to shear? That resistance, that modulus, is going to be G. And can anyone take a wild guess what that name of the constant is called? This is Young's modulus. What is G? This is, remember, this is, let me write down here. You guys can type it in or say it. This is shear stress. This is shear strain, right? Normal stress, normal strain. Any guesses as to what this constant is?
It's lagging. Everyone.
Oh, sorry. Bulk. Okay, I've seen it as bulk modulus. It's related to it. And by the way, what is shear itself? If I were to write it. So sorry again for that delay. I wonder if it's because, let's see what's it doing. Let me know if it picks up. So don't say it. Okay, I'll wait here. Sorry, guys. Let me know when you guys see it here.
Nope.
You guys see it? Screen. Let me. I'm gonna highlight what I'm asking for. So what is this one? I highlighted G. Do you guys see that? You guys can do a thumbs up or okay. It's picking up. So what is that G constant? What is that equal to eventually? Take a wild guess. It's not,
The displacement angle? No.
displacement angle. No, that's shear strain.
Oh.
Okay, so let me try again, right? So look, how do I get shear stress? You get it through the shear force, right? Gamma is called shear strain. This is a modulus, resistance. To what though? This is called shear modulus, okay? And it also has like other words, but I normally call it shear modulus, okay? So just think about number 2, chapter 2 is just about geometric descriptions, what we're trying to solve for, okay? Any questions or before we move forward? Typically when you have materials, and depending on how you look at it, let's imagine that this is a piece of rubber, right? This is an actual testing procedure. I was hoping to show that, demo that in class, but what I'll do is instead is I'll show you guys some videos. We'll watch some in class when we get to chapter 3. So this is the material that actually just pulls material, okay? So it's like an instron, right? So you clamp material down and then you stretch it, or some of them are designed to compress. Rubber is not good under compression, right? It just buckles. Concrete, on the other hand, is really good under compression. So this is before, and then this is after, right? And so the question is, what happens to those line segments, right? This line segment, doesn't it get longer? Doesn't it get stretched, right? So you have some initial. If you actually draw the line segment, you have some L final. But what I care about is what is the strain? But here's another thing, though. I want you to kind of think about it. What if, and this is assuming that when I look at this line segment, that I do my cuts normal to the material, right? My cuts are always normal. Chapter 10 is all about, well, what if I look at it at some different angle, right? when I look at, so let's kind of think about this. The force here is 10 pounds, right? I cut it on the bottom. When I cut it, don't I have a normal force? And then I have a shear force, right? What is a normal force? Just real quick. What is that normal force? You guys can type it in or say it.
10 pounds.
10 pounds, right? What is the shear force?
0.
That's right. So N is equal to 10, shear is equal to 0. So is there shear in the material?
No.
No, okay? However, there is shear in the material, not just the way I cut it. Because what if I cut it at some angle like this? Right? Where it's still 10 pounds. Now, let's say I don't have a shear like this, and then I have a normal like this. Do I now have shear? Can I say that shear is equal to 0?
No.
No.
No, right? So that's a very important point. So depending on what angle you look at it, you have shear. And what does shear do geometrically? Changes its angle, right? So now you can see that because look, the only thing that's happening to this rubber is that it's being pulled in tension, right? So the only thing that's happening up here, right? This machine is just going to pull in opposite directions, right? Pull this way. But if you look at this line here, look at this line here at an angle, right? Doesn't this line of angle kind of rotate a little bit? It's kind of hard to see, but shouldn't these angles change? It kind of rotated a little bit that way. Can you guys see that a little bit? It's hard to see, right? So that line will actually rotate as the material is being stretched, which leads to my point, right? That even though at a certain angle you can have shear in the material, depending on how you cut it, but all this whole time we've been cutting it normal to the material, right? And we're going to still keep with that. But guess what? Just be ready for chapter 10 is what if I cut it at all angles, right? We're going to develop some techniques on how to do that. Here's the reason why. Because maybe the material, the rubber, what if rubber does not fail like that, right? What if the rubber actually just cuts like that? Why did the material just fail like that? Well, because the shear stress is higher there and the material is weaker under shear. Okay, and we'll learn more about the shear modulus and all that in chapter 3. Okay, so again, I'm just trying to give you conceptually what's going on. So you have to have a good understanding of how materials behave. Solid materials, right? Good?
Yeah.
Awesome. All right, so let's kind of go over real quick the units of strain. What are the units of strain? Strain. Normal strain. Normal. What is it? Change in length over what? Original. If your length is in meters, what do you divide by? Meters. Shear strain, right? Displacement, right? Shear strain is typically radians or angles. We're going to keep it to radians. That's and then if you want to convert to angle. So what are the units then for strain, whether it's normal or shear? Meters over meters.
Unit.
No unit, right? So what is the answer?
Come
A, B, C,
on.
or D? Huh? D? Okay, so there's no unit. Also, B, right? Because you could always convert, right? What is 1 millimeter? 1 times 10 to the minus 3 meters over 1 meter. Meters cancel, right? You just have an extra 10 to the minus 3 outside. All right, so technically B is also the correct answer. I would be consistent, keep it the same units, right? All right, moving forward. All right, so here's a little a little more calc way of doing it. Imagine this is potato. So you have, this is a calculus way of looking at it, right? Because when I do my block, I do some long line, right? But calculus is all about, well, I care about the strain of every single little point, not just the line, right? I want to look at the strain of the infinitesimally small, right? So then what I'm going to do is, well, I have some change in length, right? But what I want to do is look at how my change in length approaches 0, right? Which becomes dl, right? Now, in general, L is a good variable. I'm going to start using L, but in general, what the book does and Hibbler does consistently is that any length along any axis, they use the path length, right? That's why they use the variable S. Doesn't matter. You could use it whichever variable you want, but S is in general, right? Because look at what axis it's doing. If it's not deformed, it's the N axis. I could call it the X, Y, Z, P, doesn't matter. They call it the N. So this is my potato, and this is before, and then what happens to the potato? We don't know what happens. Remember how we talked about chapter 2 is about only the geometry? Just like F equals ma, A is is the acceleration, the geometry, motion, but we don't know what forces, right? So right here, we're just talking about, okay, this is what happened to it. What happened to it? Maybe forces, moments, cause, deformation. So here's the line, right? The line itself has some initial length, delta S, right? From A to B. But then what happens to that line segment? If I pull it, right? If I pull it only one direction, it's only going to stretch into the line, right? But if I start having moments on here, if I start having moments and force loads and it's not uneven, well, you can have some arc length, right? So you want to know what that arc length is. And that arc length is like my delta, this is like my change in, so I'll do it based off of the, what we were talking about from before, right? So delta S is like my L initial, right? In quotations. Delta S prime is like my L final, right? There's a reason why the book does delta is because guess what? We're going to let delta go to what? 0, okay? So we're going to look at the infinitesimal strain. So remember how I told you, it's always, if you look at the average, just like average velocity from dynamics or physics, you look at the delta, the change in length, right? Now the thing is the strain on average is not going to be exact, right? If you want to know the instantaneous, you have to let delta go to 0, which means it becomes a ds, right? Infinitesimal ds. By doing that, you get the instantaneous strain, right? So this is called the average strain, right? Look, isn't this L final? L final, this is L initial, and then this is also L initial, right? So looking at how we define it, let me move the actual, but again, we're looking at the calculus way of defining it. This here. Average strain. So this is like our delta L, right? On top over L initial. Just to kind of be, so I can be consistent with my notes from before, the first page. Now, what happens if you let delta go to 0? So see the calculus definition is limit as B approaches A, right? Along the axis, right? These delta become what? ds prime minus ds over ds. Same idea. It's the infinitesimal, like our L final minus L initial. Okay, just to kind of be consistent. But what if you care about the final length? Okay, so what is strain? Let me kind of repackage this, right? The calculus way of doing it. Strain is your final minus your initial infinitesimally, right? Over your initial. Let me do this one first. Strain is your final minus your initial over your initial. okay? What I want to know is what is my final length, right? If I know how much my material is going to strain, I want to know if my bar was 1 meter, and I applied some force, I strained it, what is my final length of the bar, right? It's going to get stretched if I stretch it. So if I want to know my final length of the bar, all I got to do is some fancy little algebra, right? I just got to do, I solve for L final. How do I do that? Multiply by L naught, right? And then you add the L naught. Okay, so what I did on the left side is I solve for L final. I'm just going to do a little bit more. L final is equal to, I can pop out the L initial, right? 1 plus epsilon times L initial. Okay, this is going to be very similar here. If you want to do your final length, the calculus way of doing it is 1 plus epsilon over your initial. Okay, so what does this tell you, right? If you look at the formula down here, let's say you have a bar with L naught equal to the bar here is equal to 1 meter. And then strain, remember, how do you get strain? You have to have a force, right? It stretches it. What if your strain is equal to 0? What happens to you? What is your final length?
0.
It's the same as your initial, right? So, but what if my strain was positive a number? Then your final length is going to be greater. Your strain could also be negative, right? If my strain is negative, shouldn't your final length be less than your original? So you can actually compress it, okay, depending on your strain. So this is like we're gonna eventually move on to this definition, but there's a calculus way of actually doing it for all material, the continuous way. Okay. I'll pause here. Any questions or thumbs up before we move forward? Hopefully that's clear. Awesome. Okay. All right, shear strain, same idea. I kind of did it before. What if our axes are 2 of them? What if one is normal? Actually, this is the NT axis. I don't want to say it's normal tangential. It's just NT. Okay. So initially, what axis are we talking about? This is the NT axis. What I showed you before, and I'm gonna show you, right, is you can have you can have a box, right? A box was like it was like this, and then what happens is you put a force on top of it, and then the box became like that, right? So notice how the shear strain is before and after, right? The shear strain, this is what we want, right? That's a change in angle. What caused it? Some force on top, right? Some force V, shear force. Well, your shear strain is with respect to which axis here? Yes, Freddie, you have your hand up. The UT axis? Up here, though. What axis is this? Colin?
NT axis?
Yeah, so the XY, right? So then this is going to be shear XY because it's dependent on 2 axes, okay? So what was the original angle? Pi over 2, right? So notice that the definition is going to be pi over 2. I use 90, but because that's how we visualize things, right? 90 degrees. But we're going to go back to pi over 2. Just remember, pi over 2 is 90 degrees. So what happens to this potato? You're going to have forces, moments, distributed loads, blah blah blah. Then what happened to the angle, right? So notice how. So your new angle, right? This used to be your TN axis, right? Actually, the TN axis were here. They're still there. See, but what happened to those lines? They moved, right? So this is like your new angle, right? This is like our new angle. Let's say it was a box, right? So before it was 90 degrees, now it's some new final angle. But what I care about is, because it's the NT axis, right? What I care about is the change in angle, right? Isn't this this minus the angle theta prime? So again, it looks at the limit, right? I want what's happening exactly at A. If you want to know what's happening exactly at A, shouldn't your B point shouldn't B approach A, and shouldn't C approach A? So that's like the calculus definition, right? But really here, what I care about is a change in angle, right? If your final angle is 20, your original angle is 90, the change in angle is 70, right? So that's what it means by shear strain. Good? And we'll do some more examples like that kind of focus on that. Awesome. All right, so now this potato. But don't worry, potatoes exist in 3D unless you have a potato chip. Well, even then, right? So then, chip. So we care about is what is ultimately happening to a cube, right? I mean, I've been saying it from before is we care about what's happening to the cube. What's happening to the potato, right, is that you have forces, you have linear distributed loads, you can have surface distributed loads, right? You can have moments acting on it, everything happening on it. But what we care about is what is happening on the inside and what is happening to some little cube at A, okay? So in general, the cube could stretch and the cube could do what? It could stretch. What else can it do?
Shear strain.
And shear strain, right? So it can do this, it can do this, stretch, or it could do this. Change in angle. Well, the way I drew it, isn't that one face, right? How many faces are there? Six faces, right? So now, couldn't it stretch also in the X? Couldn't it stretch in the Y? And couldn't it stretch in the Y? Or Z? So those stretches in those normal directions, aren't they called normal strains, right? But couldn't you also change your angle with respect to the XY axis? Couldn't you also do the YZ axis? Couldn't you change your angle in the, what else is there? XZ axis, right? So you can have 3 strains and you can also have 3 shear strains. Does that make sense? Just before we started showing you the picture. So ultimately a cube, a perfect cube becomes what shape if you do everything to it. And you learn this in Calc 3. That is called, that shape, if I could move my mouse, that is called a parallel pipette, right? So if you throw everything at it, right? If you throw normal strain in the X, by the way, see how this definition looks like? That's to get my X final, right? It's just modified differently. My final length, right? Because isn't delta X, right? Look at the undeformed. Isn't delta X your initial? And then your final length should be this, L final, right? So, but your cube could do 6 things. It can stretch in the X, stretch in the Y, and stretch in the Z. But it could also change its angle in the Y and the XZ plane, right? Remember how we have to look at it in terms of the plane? It could change its angle between 3 of them, right? So this is like my final angle, right? Final angle in the XY, right? Because look, I'm subtracting out the change, right? This is like my final angle in the YZ, and this is my final angle in the, it's just modifying the actual expression in the XZ, right? Because look at this axis. This is Z right here. Let me zoom in on that one. Right, see how the parallel pipette is? If that's my Z y-axis, right? The ZY axis, well, isn't my theta prime for YZ or ZY? Doesn't matter, right? That's what this is, okay? So the point of this is that don't worry, we're not gonna do too much parallel pipette 3D. In more advanced courses, you will do it. It's very hard to keep track of all this information, but that's why we do more matrix algebra. So even from my grad school, we would do this type of work, but it would just work in matrices, okay? But right now we're just going to do with surfaces, just looking at what happens to a bar if you pull in 2D, okay? But remember, materials have the ability to do the same thing in 3D. Oops, I lost you guys. Is it still delayed to what I'm talking, or did it improve?
Improved.
Okay, okay. Awesome, let's see some thumbs up. Okay, cool. So I think we're probably gonna be ready to do some. Okay, that's just more data. So you guys can read that, and if you have questions, please let me know. All right, so here we go. And this is here's an example. You have a rod, a slender rod. All right, and here's where we're going to need some calculus. All right, we'll do one example using calculus, but then the rest will be a little bit more straightforward and more closer to what you'll see on the exams. But I want you to practice this calculus definition. Okay, so here we go. So a slender rod creates a normal strain in the rod of 40 times 10 to the minus 3 z to the 1/2. Okay, so let's write that down. What do we know? We know that the strain is equal to 40 times 10 to the negative 3 z to the 1/2. Okay, where z is in meters. Determine A, the displacement of B and B due to a temperature increase. So imagine that you increase the temperature, and you learn from physics, when you have an increase in temperature, there's some thermal expansion, right? There's some coefficient of thermal expansion, temperature increases, so it's going to stretch. So technically that's called thermal strain. It's strain due to heat, right? Then we're going to look at the average normal strain on average. So it's two things that it's asking for, right? What is the strain instantaneously, right? And then overall, how does it calculate the displacement? And B is on average, meaning, look, here's my bar before, here's my bar after. What is the average between before and after, right? It's not going to be exact, right? But it's going to be an average. Just like velocity, like when you're when you were trying to get to school, right, or wherever, you cared about, okay, you didn't care about the instantaneous speed at every single point, every single second, right? Even every single microsecond. That would be called the instantaneous velocity. But on average, I traveled 5 miles. It took me an hour. On average, my velocity is 5 miles per hour, right? So that's like on average. It's not exact, because maybe at times you were faster, at times you were slower, et cetera, et cetera. Same idea here. Okay, so strain, think of strain, normal strain, normally, right? Because the bar is going to get longer, is how much you change a length over your original, right? It's a measurement. It's a relative measurement over your original length. Notice that the strain itself is a function based off of Z. It's a variable, okay? We call this now, how is it defined? If you look at this, A is your origin, right? Z is a variable. So Z is the actual location, right? What if I ask you, let's say I look at point 1, right? And then you have point 2. And you increase the heat, and you notice that, look, point 1 is like somewhere over here, 1 prime, right? And then look at point 2. Maybe point 2 is somewhere over here, right? So it changes its position, right? Before, after. But what is true is, in this case, is that, look, the things strain differently, right? It's possible, actually, I'm going to exaggerate a little bit more. If both points had the same strain, shouldn't they change their position the same amount, right? Relatively speaking. So let me say that one more time. If the whole bar has the same strain, if it stretches the same amount, shouldn't the position, let's say, for example, I have a block, right? And I pull the block this way. If I have point 1 here, and I stretched it, right? And then point 1 becomes over here, 1 prime. And let's say it moved some space too. Let me zoom in on that because my sensitivity is a little bit off here. Oh. Okay, so here's what I just said here. So look, the 1 was before, now 1 was after, okay? The change in length, right, with respect to its original, let's say is 1, right, from here to here. Now, what if I draw another point 2? And then it went to 2 prime, right? If the material, if the whole thing experienced the same stretching, the same strain, then the displacement should be the same amount. It's at a different point, right? But the displacement, how much it changes with respect to its original, should be the same amount. That's where strain is constant, right? But guess what? In this example, look, strain is dependent on your actual position. So look at your position. It's a function of z, right? Z to the 1/2, or like root z. So shouldn't that tell me then that, look at 1 went from 1 to 1 prime, right? So 2 should go a little bit more down, right? It's not going to be the same amount of distance, right? Because, right? So maybe 2 went down a little bit further. Does that make sense? Because why? Isn't z at a higher position, right? Isn't z, the distance z, from here to here, z of 2 is greater than z of 1. And so if z of 2 is greater than z of 1, you plug it into this function, then the strain at that point is greater. Okay, I'll pause there. But look, here's the key thing. I care about how point B moves, okay? And I want you to think about this. Doesn't B depend on every single little particle above it? So for example, if 1 goes from 1 to 1 prime, doesn't B move also? Right? Because it's attached. Remember, it's pinned at A. A, you can't move at all. I can prove that to you mathematically. Look at at A. What is Z equal to at A? 0. So that point there, the strain is 0. So at that point, that particle is not going to move. It's pinned there, right? But then if I look at it at it further out, the B is going to depend on every single little particle above it moving, right? So, so if 1 moves to 1 from 1 to 1 prime, B is going to move because 1 moved. If 2.2 moves, doesn't B move also dependent on 2? So we have to somehow mathematically add up the total contribution of all the particles above it, because that's what's going to cause B to move down, to displace. I'll pause there and see if that makes sense. And so how do I add that, right? How do I add all the contributions of every single point? Integral. You integrate, you sum it all up. You sum up the change in length of every little single point, right? The change in length of every single little point, the distance, right? Let me do here. From if I look at the 1 to 1 prime, right? 1 to 1 prime. That is like my, from 1 to 1 prime. Didn't I say that is like my ds prime, right? Prime is my final. I'm using d now, not my delta. Not d delta here. Use d, not delta. Why? Because don't you look at the instantaneous strain of every single little particle, right? And in general, your definition was from before. Your strain in your material is equal to your final of every single infinitesimal point minus the initial of your infinitesimal point over your initial infinitesimal point. That's just 1 point, okay? So what is a change in length of, what is the final length, right? So here's the question. What is the final length of 1 little point? What I'm really asking for is, what is the final length, right, of, oops. So let me kind of draw the parallel. Think of this as, again, this is a calculus definition. This is like saying L final minus L initial over L initial, right? So what I'm saying is I'm going to rearrange that formula, the red one, right? with a ds prime, I'm going to say that this is going to be final, so the final length, ds prime, how do I solve for that, right? That's equal to your original length times 1 plus, and I think I actually drew it the other way. I'll be consistent. It's going to be 1 plus your strain, right, and your original length, okay? So ds prime is, remember, it's when 1 goes from 1 to 1 prime infinitesimal. It's very, very small. It's the calculus of the small of the d, right? But I want to know the total, every single little particle, right? And as Colin said, you're going to add it up. And a fancy way of adding it up is integrate. So I'm going to integrate, add up, not one particle, but all particles. Again, this is like the calculus way of doing it, right? So how do you add up all the particles? So then you're going to say your ds prime, right? You're going to integrate from 0 up to, what is it? We're going to add up, how are we going to add up the final length, right? Look at how your z-axis is defined, right? Don't I want the strain of all the particles from z equals 0 all the way to what? B. What is that length initially, right? That is 200 millimeters, right? And by the way, look at this. Z is in meters, right? Z is in meters. So the strain is in meters, meters over meters. So I'm going to keep things in meters just to be consistent. So when I evaluate my limit, like my L final of the last particle, right? The last particle, what is it going to do? It's going to stretch out. Also B, L final is going to be 200 millimeters or 0.2 meters. I want everything in meters. So then I'm going to integrate 0.2. For the bar, I'm going to say my bar, the initial length of the bar is L naught, right? So this is 0.2. 0.2. Okay, that's the left side. But what do we have on the right side? We have the integral from 0 all the way to the final length of the bar, right? Of 1 plus epsilon. Actually, we can convert this, right? Doesn't matter. S is in general, any axis. I want to be consistent. Let's just modify our formula. Can we just say, and there's nothing wrong with this, can we just say that this is designed for Z, right? Remember how it doesn't matter what axis? Then that means this is Z also, right? So then that my strain is going to be epsilon C to correspond for that axis, okay? So it's nothing different, right? It's the same formula. S is in general. So I just want to be consistent here. So then that changes to dz prime, my epsilon Z, and then this is dz. And there's a reason why, because look, isn't my strain function 40 times 10 to the minus 3 z to the 1/2, right? Good so far? I'll take that science as a excellent. Okay. So how do we, let's kind of do a little bit more work. So how do you evaluate the left side? Actually, I don't even know. Isn't this is what I'm solving for. What am I doing? My limits are defined differently. This Z is initial. You go from your initial to your final, right? So that's really your final length of beam. Remember, your limits are always initial to final. That's really what I'm solving for, right? I want to know what is the final length of the bar. That's what I'm solving for. So initial and final, and oh yeah. So what is then? What I should have keep it in general form. What is your initial length of the bar then? I should have generalized it before I start plugging in values, right? What is your initial length of the bar? this is where the 0.2 meters goes in, okay? On the right side is you're tracking the how much each particle, each coordinate, each position of the particle changes, displaces, right? So don't you have a particle at z equals 0? Don't you have a particle at z equals 1? There's a particle at z equals also 0.2 millimeters, right? So we have to look at that and then integrate the whole thing. Okay, so you have to integrate the whole thing. So now, what do we get on the left side? What is the integral of dz prime, or 1 dz? Here, you're just going to get L final minus L initial, okay? L final minus, what is the initial length? 0.2 meters, okay? On the right side, let me write this down, this step here, 0 to 0.2 meters. The final length of the bar, or up to where the locations of the particles, right? There's particles all the way up to 0.2 meters. 1 plus, what is epsilon z? 40 times 10 to the minus 3 z to the 1/2. dz, okay? So then how do you evaluate this? 200 minus dz, do we get that? Okay, I think you're referring to the right side column. All right, so how do you evaluate this integral? We're gonna do, what is the integral of 1 dz? It's z evaluated from 0 to 0.2, right? 1 plus, let me make sure I did this correct. Z, did I do that right? 0 to 0.2. Okay, and then we're gonna do 40 plus 40 times 10 to the minus 3. What is the integral of z to the 1/2? That should give you z to the, you add 1, right? So 3/2, and then you have to multiply by the reciprocal, 2/3, from 0 to 0.2. Okay, good, thank you. Okay, and then from here, we want to know what is the, okay, I gotta look at that number, 1 plus c. Let me double check something real quick. Make sure I'm, go ahead and try to integrate the right side and give me a value. Yeah, I gotta check my limits because I think I confused myself. Okay, I think that's my misunderstanding. So here is what is dz prime, right? By definition, isn't dz prime already the dz prime is the final length, right? So dz prime is already the infinitesimal final length. So you don't have an initial length in the definition, right? So all you got to do is evaluate from 0, right, of every single particle. So what you're doing is you're getting the final length of every single little particle, okay? So it's not initial to final. So dz prime, remember how we said dz prime is like our final length, right? Final length. So, but what we're doing here is when we integrate every single little particle, right? Because every single little particle has a final length. And if you add up every single final length of the particle, you start to add up the whole length of the bar, okay? So it should be 0 to L final, okay? And that should fix it. So this is 0 minus, right? L minus 0. And I think there's some comments in the chat. Let me double check that. Hopefully that cleared it. Yeah, so the rod should be in the final state, the final length, okay? So if you look at this, then this gives you 0.2 meters, right? And this is like this is where the initial length is, right? When you integrate just that, that's the initial length. And then this length here, this is your delta. It's like my delta length, right? Your change in length. And so I think if I can deduce that from your answer, Luke, this is 0.02385 meters.
Yeah.
Okay. So, and that kind of, and that makes sense, right? So what we're doing is the change in length is how every single little particle changes its length. But each particle changes its length differently, right? Depending on its position. So that means because it strains differently. So you add up every single little particle, its contribution to the original length of the bar. And that makes sense, right? Because look, L final is equal to your L initial plus your change in length. Not L final here. It should just change length, right? Because look, if I modify this, isn't your change in length equal to L final minus L initial? So the final length is 0.202385 meters. So that's how much the final length of the bar, point B displaced. So is the final length of the bar, final length of bar. And that's how much point B displaced, how much it changed its position, right? Because it's located there. Any questions on that? So that's the instantaneous, right? That's every single little point did its contribution. Hopefully that answers your questions, everyone. Okay, so B, what is the average normal strain on average? So epsilon average is that definition I've been using, right? L final minus L initial over L initial on average, because remember, at different points, it's going to stress differently. But now what happens is, now I know my final length, I know my original length, and let's just find the average between those two states, not the in-between states. The problem that we did before is everything in between, okay? So the final length of the bar is going to be, what is the final length of the bar? It's going to be 0.202385. Oops, that's the change in length, right? So the final length of the bar, oh no, that was right. Get closer here. So the initial length of the bar, or the final length of the bar is 0.202385 meters. The original length of the bar is 0.2 meters. And then what is the original length of the bar? 0.2 meters. And notice how the meters are going to do what? Cancel. So this is on average how much it's strained relative to its original. Some points stretch more than others. A didn't even stretch at all. So what would that value be? And then Colin, you said because 0.22385, you put an extra 0 in between. So should it be? Let me see. So what is the change? Actually, what is the change in length? What did you guys get? Was it 0.02385 or was it 0.238? I think it should be a 0. Okay. Yeah, I think because the thing is, the confusing part is that 0.2 is already meters, right? So you have to have that 0. Otherwise, you're going to make it the bar 0.4 meters. Okay. So on average, what was your strain on average? You have your final length of the bar, your initial length. How do we? Yeah, what do you get there? Uh, 0.012. Okay, let's get a little bit more exact. Yeah, because what's going to happen is strains are now going to be small. So let's try to be accurate as we can. So 0.011925. The units are going to be meters over meters. Okay, or if you want, millimeters over millimeters. It doesn't matter. But I want to put it in this form. And let's do it in 3 sig figs. 1.19 times 10 to the minus 2 meters over meters. So that would be the average strain. Again, different from instantaneous, right? Instantaneous goes back to the idea of what is your velocity going to school, what is your speed, and what is your average, right? Because you have an instantaneous, and then you have on average. And I'll pause here in case anyone has questions. So this is like a calculus way of doing strain, right? Of every single point of every single particle. Notice that it's normal strain, right? Because it's the stretching is perpendicular to the surface, right? It stretches out. 0.22385. 0.2. Oh, I see what you're saying. Yeah, you're right. Oh, sorry. The final answer. That's right. Thank you very much. I'll just move that over. That is correct, right? Let me go a second. I'll just move it over here. Is that good, everyone? I think that should be fine. Unless I'm wrong. Get a second, a third. Okay. Yeah, so it's actually the other way. Sorry. Colin, I think you might want to double check the math. Let's see, what could it be? 80 over 3. Yeah, just double check that. I think del is 0.002. Thank you, Jack. Okay. Any other questions? We're good? Check. All right.
Hey, I have a question.
Yeah.
Why is it necessary to keep meters over meters? Like, can't you just ignore them?
Because it's good practice to keep them. Because let's say I asked you, well, find the final length, right? So if I look at what the final length is L initial 1 plus your strain. Actually, this case is probably not a good example. It will be important in chapter 3. Chapter 3, when you have the Young's modulus and strain, if you preserve the units in strain, and I ask you what is the how much did the bar strain due to some force, you'll preserve the units even though it's unitless. Okay, good practice to just keep it in there even though it cancels out. Plus to remind you, wait, what are the units again, right? So it'll keep things consistent, because if this is in meters, right, then make sure these are in meters over meters, right? Because if this is in millimeters over millimeters and this is in meters, you're going to have an extra term that comes out, like a 10 to the minus 3, right? So as long as you're consistent and do that throughout, it's good practice, okay?
Well, one question, Professor.
Yeah.
That answer is that expansion is the final expansion, or is it expansion at one point only?
No,
Is
it's
the
everything.
average.
It's
Okay.
the average of everything, every single point.
Okay.
Like for example, if I go to the bar, right? If you look at the function, if you look at the function for z, look, what about the particle at a? What is its? How much did it change its position?
Nothing.
Nothing. But if you look at a point B, how much did
Yeah.
B itself change position?
Yeah, that's the answer. It's going to be expansion.
Yeah, so B changed the most. A particle here probably changed a little bit, right? But the further you go out, it starts to stretch more and more, right? So every single point stretches differently, but point B depends on everything above it, right?
Okay.
So you can look at the instantaneous strain at every single point, which is what we did the calculus way. But on average, what is the overall average strain between its final length and the original? Okay, so it's different ways of saying it. The analogy is instantaneous velocity, average velocity, right? On average, how long did it take you to get to school? Or velocity, what is your velocity at every single point, at every single time, right?
Okay.
At 0.00025 seconds. That's instantaneous, right? Every single point.
Yeah, I got it. Thank you.
Cool. All right. We have what caused the bar to stretch? It wasn't necessarily forces, right? It wasn't necessarily forces. It was thermal, right? But the direction in which it stretches typically is in when it stretched, it was straining, right? It's a normal strain. But now the other thing that we talked about is, and I kind of we talked about at the beginning is, well, what happens if you have some force acting on this plate? So see the blue box? That's before, right? What happened now is we'll look at the box after. So the dash shape is, what shape is that? That's a parallelogram, right? So what caused it? Maybe there was a force on top of the plate causing it to some 10 pounds, right? So I have some force on top of the blue box. It's going to change its angle, right? So the question now is asking, right? Due to the loading, the plate is deformed into the shape shown. Determine A. There's two things that we're going to do. The average normal strain alongside AB and the average shear strain. So I'm getting two pieces of information, okay? And let's kind of decouple each one. So remember, and there's a reason why I drew that box and I drew a line, right? What happens to that line, or even if it's on the potato, what happens to that line before and after due to normal forces, right? Or due to anything. And then the question is, the next thing is, what happens to the rotation? What is the angle? So different points, as you saw, can strain differently. And what I mean by strain is both shear and normal, right? So the first part, let's look at part A. Okay, so what it's asking is on average, not the instantaneous, on average, meaning average means delta, right? So you look at a large segment, a large line. So what it's looking for is, well, first of all, what is strain in general? Strain is final minus initial over initial, right? Even if it's average or instantaneous, I can modify that, right? But just think of it as final minus initial quantity over the initial. So here it's saying side AB, okay? So what I'm going to do is looking at it for side AB. So remember, before, after, right? So the bar, we don't care about anything before, during, in between. Just like the bar, we actually compensated for the between. But here, we're just going to look at the, that's why it's average, right? We're going to look at the before and after. So I'm going to zoom in, okay? So line segment AB. So line segment AB is this line segment. Do we all agree? Okay. So that's a line segment. Imagine that you get a green Sharpie, you draw a line on the box, that's the line of the box. What is the length of that line?
$250.
250. Thank you. Now, what happens after? What happens to that line segment after? Look at point A. Does point A remain the same location after?
Yes, point A does.
Yes.
Yes. How about point B?
No.
No. Thank you. All right, so B goes to B prime, right? So now we have a it's not a parallel curve. Here, let me try something here. Try my best. Okay, so you guys see that? We went from B to B prime. So can you measure the final length of the AB prime? Does it get shorter or does it get longer? Does the line segment, if you get a measuring tape, right? If you measure that, is it shorter or is it longer? How are you able to do that? So Colin, it's only the same distance if it's a rigid body, right? If it maintains its shape. But remember, materials can compress or stretch. So most likely it's going to be shorter. So we expect the strain is going to be negative, right? It's going to change its length negatively. And the final length is going to be less than 250, okay? So how do we do this? This is where the geometry comes into play, right? Because we already have most of the information. And let me be very specific. So it says here, what is the average normal strain, right? So the average normal strain of AB. So the average strain of line segment AB. We're going to modify the formula like this. Well, what is the final length of LAB prime? I'm just going to use the general definition. Well, we have to figure that out, right? Length AB prime, right? That's the final length. Minus your original length, right? What is a good variable for original length? Length AB, right? And then what is your original length again? Length AB. Well, the good thing is that we already have most of that information, right? We already know what LAB is. LAB is given 250 millimeters, right? Trick is, what is LAB prime? What is the final length of that? And let me zoom in here a little bit. Oh. How do you find LAB prime? Triangles, yes. Angles, okay, so that's what it's going to be. So let me show you something real quick. What distance did this corner offset here? What distance did it offset on the top right corner? So shifting to the right is 3 millimeters, right? So then what do you think the shifting to the right of from here to here? What distance is that going to be? 3 millimeters. Does that make sense? Okay. How much did it shift down on the right top right corner? 2 millimeters. How much do you think B is going to shift down? 2 millimeters. Good. So here I'm going to zoom in on this, okay, just so we can be a little bit more accurate, because it looks sloppy here. Yeah. Let me clean this up real quick. Okay, that's 3. From here to here, shifting of 2. Okay. In general, you can actually use couple techniques. You can create a triangle. See the green triangle? You can close off the triangle and do this triangle, right? When you have a triangle where none of the angles are 90 degrees, I recommend you use law of cosines. But in general, to make your life a lot easier, always refer to a subset of law of cosines, which is Pythagorean theorem. Pythagorean theorem means that you have one angle that is 90 degrees, right? It's a subset of law of cosines. So what I'm going to do is make a triangle. Forget that green dashed one, right? I'm going to make a triangle such that it has one corner that is 90 degrees. So here's my triangle. Triangle is going to be, I'm still going to start from here to here, right? And guess what? I want one of the sides to be AB prime, because isn't that the length that I want? Does that make sense? So this length here of the triangle, this length here is LAB prime, right? What do you think this length is here? That's 3 millimeters. This length is here. The whole thing is 250. Let's take out a chunk of 2 millimeters. That gives me 248, right? You could have done the green triangle one, the complete one, but it requires a little bit more work, right? You have to find an angle. But you can still do it. But here I made my life easier, because what I do know is that LAB prime squared is equal to 3 millimeters squared plus 248 millimeters squared, right? And then if you do LAB prime, you solve for it, you do the square root of all that, right? A squared plus B squared, 9 plus 248 squared. And what do you get there? And let me copy it again. Let's see. Okay. So notice how we have to be as accurate as possible, right? Because the numbers are very small. In the final answer, 3 sig figs, make sure you put it as 3 sig figs, okay? So we're getting 248.0181445 millimeters. Okay. So notice how it's actually shorter, right? Shorter than the 250. Okay. All we got to do now is plug it in. That's it. We're pretty much done. Because what is a final length AB prime? And notice how this is based off geometry, right? That's essentially what strain is right now in this chapter. We're going to get 248 7.0181445 millimeters minus 250 millimeters over 250 millimeters. And then what do you get here? What is the average normal strain? What is epsilon average? AB. Keep it as accurate as you can. .004, and never mind. .00768, .00768. So there's some small deviations there, getting different ones. .7927, David, and okay. So I'm gonna go with that 7927. Thank you. So it's gonna be negative, right? Negative 7.927. So this could be 7.93 times 10 to the minus 3 millimeters over millimeters. It's unitless. I'm preserving it. Okay. Let me kind of redraw the red triangle so it's easier to see. So the red triangle that we created is a custom one where this is 3 millimeters, this is 248. Any questions on that part? So again, we don't know what caused this, right? Maybe it was some forces that are normal, or maybe some shearing forces, but that's what happened. Chapter 3 is what caused it. Okay. Let's see. We'll do this one and then we'll take a break. Okay. Here's the question now. What is the average shear strain in the plates specifically at A relative to the X and Y axis, right? So now what I want you to remember is shear strain is angle change, right? What was it before? What was it after? So wasn't the angle, so it's asking exactly what is happening at point A. So I'm gonna zoom in on it again. Okay, so shear strain on average. So what is the definition for a shear strain? Shear strain in general is equal to pi over 2 minus theta prime, okay? This is your, let's kind of define this. This is your original angle, right? Because remember how when you have two coordinate systems, remember it's y relative here, it's y relative to x. It's two coordinate systems that we need, like the nt axis. So that's 90 degrees. And then this is the theta prime is your final angle. So then shear strain should be your change in angle, right? And that's really what it's asking for. On average, what is the change in angle? Not as it's moving, but in the final state, right? When you look at the final and then you compare it to the original, that's like on average shear strain. So let's look at the picture, okay? So this is because it's between, and this I'm going to do the notation, right? The question is asking, what is the shear strain within the X, Y coordinate systems at point A? Where's my mouse? At point A, okay? So we need to figure out what theta prime is. Okay, we already know the original, it's 90 degrees. Okay, so I'm hearing some suggestions here. Where was I? Okay, so now let's think about this, all right? I'm gonna zoom in on the picture. Okay, the blue box was originally, it was originally this angle theta, 90 degrees, right? So this angle here was 90 degrees. Then didn't the dashed box, right? The parallelogram, isn't this like our new final angle? Isn't this my theta prime, right? So it's gonna involve, to find theta prime, you might have to create another triangle like this, right? You might want to create, or if you want to find, if you can find this space, well, this space is already 300, right? You already know this leg here. You might have to find this length here, and then you can use law of cosines, right, to find theta prime. But I want you to understand what the definition of shear strain is, and repeat after me. Shear strain is a change in angle, right? I didn't hear anyone. Even if you muted yourself, I still didn't hear. Thank you, Robert.
Angle.
Change in angle. Okay, thank you. So if you look at the triangle, right? Before it was 90 degrees, after it was a theta prime. Well, isn't this your change in angle here? This triangle? That by definition is called shear strain, right? So then you go back to your triangle. How do you find that angle, right? This is what I just said. This angle here is gamma xy. This is 90 degrees here, right? How do you find that angle? And then, Roberto, this is what you said, right? Tan theta. So tan theta being gamma xy, right? So if you look at this, remember SOHCAHTOA, TOA, tangent of your angle, what is your angle? Gamma xy, right? Is equal to opposite over adjacent, TOA. Okay, let me move this down. Okay. So what is the opposite value? So tangent of gamma xy. Make sure your calculators are in degree and radian mode, okay? Opposite, 3. Adjacent, 248. I want to explain something to you. This is called the small angle approximation. When you let tangent delta theta, okay? Tangent delta theta is equal to sorry, give me 1 second. Tangent theta is sine delta theta over cosine delta theta. Okay, this is what's going to happen when you let delta theta, this is called the small angle approximation. When you let delta theta go to 0, when you let the angle go to 0, tangent delta theta approaches delta theta. Okay, because you guys can look it up, small angle approximation. Okay, because guess when sine of theta, right, over cosine of delta theta, right? When cosine of when delta theta goes to 0, what does cosine theta become? That is 1. When sine delta theta goes to 0, that just becomes delta theta, right? That's why tan theta goes to delta theta. So I'll prove it to you, okay? So I want you to compare this. I want you to compare this, right? Normally you would do this. Well, gamma xy is equal to inverse tangent of 3 over 248, right? But here's what I just proved to you. Well, not proved, but this is the result of the proof, is that forget the tangent, ignore that step. Just say xy is equal to 3 over 248. What do you get in radians for both of them? Compare. David, Leon, I think 89.3 is your, that C is a little too high. I don't know if that's degrees. I don't know if that's the final angle or that's the change in angle. And notice that these are millimeters over millimeters, right? Which is unitless. So I want you to give me the result. Inverse tan, 3 over 248. Make sure you're in radian mode. And then what is gamma equal to when you just do 3 over 248? What's faster?
Same.
Same thing, right? So as long as the angle is very, very small, right, approaches 0, it's exactly that. The bigger the angle, it's going to deviate a lot, okay? But 3 over 240 is a very small number, right? But what do you get? What is that value?
0.01209.
0.0 what?
120,969.
Okay, so the final answer, we'll put it two ways. We will do it. Okay, so now here's what is a shear strain XY at A on average, right? It's going to be, let's put in 3 sig figs. 1.2. Oops. This is going to be 1.21 times 10 to the minus 3. Minus 2 radians. Okay, so now I can actually, in the final answer, I can approximate it. Just for funsies, before we go on break, I think you got that right, Angela? Right, thank you. Let's convert that to degrees. What would that be in degrees? So let's use a more exact one, right? 0.12, oops, 0.012069 radians, right? Now you know that 2 pi or pi doesn't matter. Pi radians is how many degrees? 180. Grads cancel. So whatever this value is, multiply by 180 over pi, and it looks like, Luke, you get 0.693 degrees. So it's a very, very small angle, right? Unitless, rads, right? But keep it as rads. So just the same reason when you normal strain meters over millimeters or millimeters over millimeters, here keep it as rads or degrees. But by default, keep things in radians, okay? So it's a very small angle change. Okay. Any questions? Does that make sense? It's mostly geometry, these problems. It's not too bad. Where's my little window? Okay, so I'm gonna reconvene in 20 minutes. And then we will do more examples unless you guys have questions. Let me see, what's the next one? We have a couple more. No, one more. A couple more. We'll do, yeah, a couple more. Whatever we don't finish, we'll carry it over, but then we'll start to chapter 3. Okay. So 20 minutes. Sound good?
Okay.
Okay. 20.
Can you go back to the previous example? Sorry about that.
Yeah. Let me go back. I'll leave it on here.
Thank you.
Yeah. So again, these are the notes too. They're being annotated, right? You can go back to that link of notes. So BRB. Yeah, And we're back. All right, let's do this. We'll finish up this problem and see how far we get with the next one. And then we'll continue with the next chapter on Monday. Okay? We're all good? We're all here? Okay. So here's another example. You have, I'll read the problem statement. You have two wires that are connected together at A. If a force P causes a point A to be displaced horizontally 2 millimeters, what is a normal strain developed in each wire? So it makes sense that if I pull it with some force, we don't care about how much force, we just care about what happened, right? The displacement. What is a normal strain? And it makes sense that the cable itself is going to get longer, right? So one thing to note is that because of symmetry, we can actually split this in half. And we can look at the top half or the bottom half because because of symmetry, they're both going to strain the same amount. So the problem says that point A displaces horizontally 2 millimeters. So let me kind of denote that on the actual diagram here. So let's imagine that point A displaces 2 millimeters, which is A prime. So it went from here to here in 2 millimeters. Okay, so then the cable itself is connected from C to now. Let me see if I can make sure I join the same point. Okay, so notice how the cable stretched horizontally 2 millimeters, okay, to the right. Put on see the chat here. Okay, so we have like a new triangle, right? The original length of the cable is 300 millimeters. So let me redraw that. So we have copy. So just kind of redraw what's happening here. Gotta draw that one. It's okay. Try one more time. Draw this line segment here. And then Draw one more. Here. Here. Okay. So we draw this over here. Okay. Let's denote some things. It's kind of what we do know. So this is point C, right? This was originally point A, and now this is A prime. The angle here is 30 degrees. Do you know the angle inside here, the triangle? You zoom in on it.
150.
Excellent. So the angle in here is 150. I'm going to cheat a little bit and make it bigger. Scale this. Okay, so the inside angle is 150. So what happens? Okay, I'm doing my best to draw in there. 150 degrees. All right. A prime. Okay, so now what was the original length of the cable? The original length of the cable was 300 millimeters. Okay. The displacement of A to A prime is 2 millimeters, right? So what can you use here? What technique can you use here? So we have a triangle. Remember, in general, if I have a triangle, base A, base C, and I have the angle between them, right, I can get C. You can use law of cosines, because isn't this, don't we need this? L, we'll do LC A prime. Isn't that the final length? We already know the original length because it's saying, we already know the original length, LAC, right? The original length is 300. What we really need is LAC prime, the new length. Because when we find the strain along the cable, it's equal to final in general, and you write it in general, final minus initial over the initial. So that requires us to find, okay, what is the final length of the cable? LAC prime minus the original length over the original length. Okay, so again, here comes geometry, right? I can use law of cosines, but there's gonna be a faster way. Okay. Law of cosine says if I know two legs, I can get the third leg if I know the angles between the first two legs, all right? So I know leg one is 300 millimeters. I know the other leg is 2 millimeters, and the angle between them is 150, right? So let me write down law of cosine. C squared is equal to A squared plus B squared minus 2AB cosine theta, right? So if I wanted to know LAC prime squared, I need 300 squared plus 2 squared minus 2 times 300 times cosine of 150 degrees. Make sure it's in degrees. 150. Okay. And then I want to get rid of the square root, so I'm going to do all this to the 1/2. And what do you get for LAC? LAC prime. Make sure it's in degree mode. Okay, thank you, Jack. We get 300.871 millimeters. Cool. So that's it. So then once we have the final length, then we can say strain AC is equal to, what is the final length? 300.871 millimeters minus the original length, 300 millimeters of the cable, one of them, over 300 millimeters. Notice that the strain here is going to be positive, right? Because the cable is going to get longer. So then, thank you, Frank, for confirming. What do you get here? What is the strain in 3 sig figs? 2.7, 2.70, 2.70 times 10 to the minus 3 millimeters over millimeters. As much as I like law of cosines, it's a little bit more work, right? Why do law of cosines when you can make triangles 2.7 or 2.9? 2.9? Okay, is there a second for that? Second and third? Okay, cool, thank you. Let me just modify that one. That just made it worse. .90. Okay, thank you. So for the, what's a better way to do it, right? As much as law of cosines is good, an even simpler way is to use Pythagorean theorem. Why don't we make a triangle? We aren't missing a 2 in the law of cosines. We should be. Oh, we are. Oopsie. Why isn't there? Yeah. The 2 is not the same 2 from that one. So 2 times a, oopsie. Hopefully you guys saw that, right? So this should be a 300 times 2. Good catch, Colin. Oh, it was Luke. Luke caught that. Yeah, so there is a 2 there, right? Because the 2 is for the law of cosines, but then 2 is for the distance too. Good catch. So now what do you get? 7,337. So sorry about that. 7,337, 079. And then we'll just modify this real quick. That's right, good catch. 300.7337. 337 7,337, and then you get 5.779, 5.779, which gives me 5.78 times 10 to the minus 3. Cool, thank you. Okay, here's another check for that number. Could have probably caught it this way. So why work with law of cosines, any triangle, when we could work with a special triangle, which has, it's a right triangle, right? Pythagorean theorem. So why don't we make, because this is this distance. This is LAC prime. LAC prime. Let me zoom in on this, and we'll do it on the side. So this is a faster way to do it. Well, can I make a triangle, a right triangle, right? Can I go down this way and then go to the right all the way to here and then define this triangle here? Okay. So the distance, so the green triangle, right? Let me highlight it here. There's the right triangle, right? You see the on the corner. So what if it's this triangle here, right? This being LAC prime, right? Well, we have a new base, right? The what was the actual? Can I calculate the actual distance, the base of it? How are we able to do that? Oh, okay, we have an adjustment. Let me double check. And you will see the actual value too here. So you're saying 301.733, 301.733 right here. Okay, with that extra 2. 300 and, okay, so 5.78 will be fine. Catch, so then, but the LAC prime is off, right? LAC prime should be 301.733. Okay, so 301. So 301, let me correct this one. 301.7337079. Is that correct? Okay, and then the final value is fine. Okay, and then Jack, so you're right. So look at the angle, right? You have the original distance, right? You know, originally, couldn't we find this distance here? The original triangle. Let me zoom in. So there's a smaller triangle right here, right? Where the hypotenuse was 300. You see that one? So if I know the hypotenuse of 300 and I know 30 degrees, well, isn't this here, isn't this piece here 300 cosine 30 degrees, right? But then what happened to A? Did A get displaced 2 millimeters to the right? So that, and then became a longer stretched out triangle, right? So then this triangle length on the bottom is 300 cosine 30 degrees, right? Plus 2 millimeters, right? Because it shifted over a little bit to 2 millimeters. Now, how do you get the other leg of the triangle, right? Knowing before, right, and after. Isn't the length vertically the same before and after? So then I want the opposite of 30 degrees. I know the hypotenuse, right? So I'm going to do 30 sine 30. Thank you, Jack. Correct, Colin. Okay, so this is going to be 300 sine 30 degrees. Okay, so this allows me, this triangle allows me to now just solve it using Pythagorean theorem. Because if I want to know what is LAC prime, it's equal to square root of 300, the base squared, quantity squared, plus sine theta squared. Okay, and then what do you get there using Pythagorean theorem? Let's see if that's clear. Theta being 30 degrees. Let me take that back. 30 degrees is the original triangle. 30 degrees is the original triangle. It makes sense that this leg is going to get longer, so that angle is going to get smaller, right? If you maintain the same height. Let me focus on here. 300. Let me fix this up. 300 sine 30 degrees. Quantity squared. Okay. All right. So Frank, you got 301.7337079. Is that the same thing? I have a bad memory. There we go. Same thing. Make sense? Good to go? Any thumbs up?
Yay.
All right. Sounds like we have Ice Cube on the line. We're going to the next problem. Any questions on that? Geometry? Okay. I have for like 10 minutes or so. All right. Okay, and this is something that I would give on more of these types of problems with the squares is something I'd give on an exam or a quiz, or you'll see in this also in the homework. So if you can get this down, you'll be fine. Which, by the way, I'm still working on your stuff. I'm going to get it up ASAP. So here we have a rectangular plate. So notice how there's normal strain, and there's also shear strain. Normal strain, stretching. What happens to the line segment before and after? Shear strain, change in angle, okay? Before and after, and it matters at what point. What's this here? Average. Okay, average. So here we're looking at, okay, a rectangular plate is deformed into a shape shown by the dashed lines. So the tan box is before, the dotted line is the after, okay? So it's asking for two things. One, it says the average normal strain along diagonal AC. So before, the problem was that we actually looked at a side leg. We could also look at the diagonal, right? Remember how when I drew stuff, I could always, what if I look at this line segment, right? What happens before and after? I can look at this line segment. It doesn't matter. If you want to look at every single point, then you have to use a more calculus definition, right? So the first one is asking, what is a normal strain? What is the variable for normal? Epsilon. Along where? AC. Okay, that's the definition. In general, what do we say? Strain is final. Here's another way. Change in length over original length. What do I mean by change in length? Final minus initial over initial. Okay. Because we're talking about line segment AC, we're going to say this is, well, first of all, where is AC, right? Let's draw these line segments before we start denoting it. Let's say I'm going to zoom in on here. I'm going to zoom in. Okay. Is that too close? If I draw a line from A, KB flexibility, oh, be nice. Okay. Oh no, almost. A line from A. A to C. Fix this real quick. Okay, so it's exactly on top of each other, right? So that's before. Then what happened to the actual rectangle, right? It became like a weird parallel pipette, right? So then the line segment ended up being, well, A before is at A after is at A, right? That corner is still there. But C went a little bit to the top right. So this corner here is C prime, right? So then my line segment stretched. Okay, to here. Okay, so notice that the lines are not aligned, or they're not collinear, right? So they're not along the same direction. So they're different. So the blue one is called, the length of the blue one is called LAC. And what happened to the green one? That one is LAC prime. Is that clear? Before, after. So then, what is my strain along that AC? Along that line, how much did it get stretched by? It should be longer, so it should be a positive strain. So then we're going to do final minus initial over initial, okay? The final one is going to be a little bit more trickier, okay? But what is my initial? Look at the box originally. What's the base distance? 400. What is the height? 300. This is a 3, 4, 5 box, right? So then the hypotenuse is 500 millimeters, all right? I'm not going to do the Pythagorean theorem. So then LAC is equal to 300 squared plus 400 squared, right? Giving me 500. All right, so LA final, which we're going to figure out right now, minus 500 over 500. Okay, my hint for finding LAC prime, the new triangle, or the new length, the take-home message is this. Yes, you can create any type of triangle with law of cosines. You can make this triangle, but I'm going to delete it. You can make this one. You can make the dashed one, right? With the green one. It kind of overtakes it. So you can make, let me draw it one more time. You can make this triangle, right? With the green one. But the problem with that triangle is that you don't know those lengths, right? They're like hypotenuses of another triangle. That's going to be a lot more work. And this angle is not, this is not 90 degrees, okay? That requires you to do law of cosines. That requires you to do more work, which we're trying to avoid that, right? Not that we're not capable of it. My recommendation is make a box, a rectangle, such that the diagonal is part of that box or the rectangle. Because if it's a box, the box or a triangle has a 90 degrees. That allows me to use law of Pythagorean theorem, okay? So here's what I just said. I'm gonna make a box such that the hypotenuse is LAC prime. So here's one corner of the box, and here's the other. If it's nice to me. Okay, here we go. Come on. No. Try one more time. You gotta be nice. You gotta be nice. From here to, come on, right there. Oh no. What the hell's going on here? My computer's going crazy. Unless someone's hacking. Y'all still here? I'm gonna do old school. Okay, so here, here's that. Okay, so what did I just do here? I created a rectangle such that the diagonal of that rectangle is what? LAC prime. So if I can just figure out those base legs, I can solve for it, right? So now what is this distance from here? What is the height of this big rectangle? And then what is the height of this, or what is the base of this rectangle? The red one, the big red one, right? So if you look at the height of the big rectangle, well, originally it's 300, right? but if you look at on the right side, you take away 200 here, right? Actually, no. So you go from here, from the base here, up to here, you go 300, right? Because that's the original distance, 300. But then you're gonna go 6 more to here. So then this here is 306. 306 millimeters. All right, so what about the height? That one's gonna be, well, from the originally was 400, then I'm gonna add 6 more. This is 406, okay? That's it. So now if you wanna know what is LAC prime, LAC prime is equal to base 406 squared plus 306 squared. Square root of that gives you your new length. So see, the trick here is make your life easier. Use triangles or rectangles, right? Squares or whatever, so that you can use Pythagorean theorem. And what do you get for LAC prime?
508.
508? 508 point what? It's gotta be more, no?
4.
508.4? Is there a more accurate? Yeah, let's do the more accurate one, because it matters. Our numbers are gonna be a lot smaller. 508.404.014. Is there anything else? Luke, you say the position vector, that's the same thing, the magnitude of the position vector. You're talking about the coordinate, right? The coordinate, same thing. 141414162. So again, let me just remind you, try to be exact as you can, whatever your calculator gives you in your pre-steps. That way you plug it in, right? When you do the actual value, 508.4014162 minus 500 millimeters over 500. And so what is strain along AC equal to? It should be positive because it gets longer. Okay, 1.68.
Yeah.
Thank you. Millimeters over millimeters. Okay, so we'll stop there. I want you to think about this, the shear strain, okay? Look at how the box used to be. And here's my tip. Look at how the box used to be. It used to be 90 degrees, right? But now, didn't it change some little chunk right here? Didn't it change some little chunk? Right? This is your new angle in between. That's theta prime. But I need this chunk, and I need this chunk, and add them. So I'm going to call this one gamma 1, and I'm going to call this one gamma 2. How do you find that angle based on this geometry? Because the total strain at A is going to be equal to those two. So your goal is to figure out what that angle is or what that ratio is from the geometry, okay? So try that out. Monday, we'll finish this one up, and then we'll start chapter 3. Good? Sounds good?
Yep.
Awesome.
Yes, sir.
Please be safe out there. Take care. I'm going to post the video as soon as it gets processed. I'm going to post it online in case you want to refer back to it. Also on Canvas, there's like let me see if I can share it real quick. Okay, I'm having trouble, but just go on Canvas under online communications. There's like virtual office hours. So I've been trying to use more of a Cranium Cafe. So if you want to have like specific questions or you can't make the office hours that I have, like typically right now it's 9 to 10 in the morning, Monday through Thursday. But at any other time, right? If I'm not in class, if you can actually knock on my door. It's a digital door. and you can ask to see if I'm available, and if you want to do like a little like a one-on-one session or a group session, whatever it may be. So check that out. I haven't played around with it as much, but try it out. Let me know if you still have questions, and yeah, just be safe out there because the next couple of weeks are going to be pretty crazy. Okay, so take care.
Take care. Okay, thank you.